Okay, let's get started. Hello, everybody. Welcome. Thank you for coming. We're very excited to be here. So this talk is about ransomware, key management, and the crypto API. Basically, we all know what ransomware is and what it does, but during this talk, we want to discuss the intricacies of key management in ransomware, discuss why that's important, and then discuss exactly how it is implemented in terms of crypto API functions on the host. So this is the agenda or the structure of the talk. We start with a little bit of an introduction, and then we go ahead and discuss a particular key management scheme or a key management model known as the hybrid scheme, which is employed in modern ransomware. And then we move on to the implementation details, where we'll look at the details of crypto API, the cryptographic service providers on a Windows machine, and CNG and things like that. And then finally, we will take the NotPetya ransomware, disassemble it, and try to understand the crypto API functions as they are being used in the NotPetya ransomware and all, and that are being used in all, basically almost all modern ransomware. Finally, we kind of put it all together in form of a ransomware pseudocode, and then we conclude the presentation. So a little bit about us. I'm Pransh. I'm a PhD candidate at Michigan State University. The dog pictured is my 1-year-old puppy. She's a Dalmatian. Her name is Gabby. And her favorite thing to do is bring me a rope to play with, to play tug of war with, and especially when I'm working on something important, like if I'm creating a presentation. So if there are any imperfections in the presentation today, we're going to blame it on Gabby. All the work that I do with my advisor, Dr. N-Buddy. When he's not in his office, you can find him surfing or canoeing or playing hockey. So let's talk a little bit about why we're still discussing ransomware in 2018. It's such a 2017 thing, isn't it? Well, not really. The truth of the matter is that cryptojacking has overshadowed ransomware quite a bit in 2018 because the same set of cyber criminals, financially motivated ones, go for cryptojacking that have interest in ransomware. So basically, cryptojacking is a little easier than ransomware because of the acrobatics involved in terms of encryption routines and basically things we're going to see in this presentation. It's just easier to do if you can download a mining malware covertly mining on someone's computer. So that's why I believe that cryptojacking has stolen a lot of ransomware's thunder in 2018. But we're still seeing instances of ransomware like SamSam, which SamSam is important for two reasons. One, it's changed its attack vector from the normal phishing and exploiting a vulnerability like Eternal Blue to actually exploiting weakly secured RDP sessions. Also, it is a targeted attack. So as opposed to the generic spray and pray kind of an approach that ransomware have used in the past, SamSam chooses its targets wisely. So these are just news headlines from about a month ago about ransomware. So the point of this is that ransomware is still very much alive and kicking. So we all know the necessary elements of a ransomware. I'll go over this very quickly. The first thing is infiltrate the computer. There's a lot of attack vectors here. You can do social engineering, phishing, or you can exploit a vulnerability like Eternal Blue and spread like a worm, or exploit weakly secure RDP sessions. So whatever you need to do to get into a host. Now, the next thing to do is acquire an encryption secret. This is very important because you need to have a unique encryption secret per victim. Because if you had the same encryption key, let's say for every victim, then victims would share keys among themselves, and that would compromise the whole ransomware campaign. So you need to have a unique encryption key per victim. So it needs to somehow acquire that. Once it acquires that, it goes ahead and uses it to encrypt users' data, and then demands a ransom. So that's pretty straightforward there. But exactly how is key management important? So key management is crucial to a ransomware operation. Just like any other cryptographic operation, key management lies at the heart of ransomware. The fundamental constraint on a ransomware operator or developer is that the attacker needs exclusive access to the key to have leverage over the victim. And it is complicated. It's not always easy to do. Ransomware developers are known for cargo cult programming, copy pasting, and they're known to make mistakes. And in a study done, only about 6% of the 1,300 ransomware that variants that were studied, only about 6% were actually effective. So we know that they make mistakes and they get key management wrong. So if we understand it better than they do, then we have an advantage. So we assume that ransomware will always find victims, and finding flaws in key management will help us recover files without paying the ransom. So that's our motivation. The evolution of key management, well, we're only going to discuss the hybrid encryption scheme during this talk for the sake of time. But basically, key management has evolved quite a bit in ransomware variants, starting 2005, 2006, when GP code and such ransomware were first coming out. The way they implement key management now is a little different and has evolved. If you want to read the details of the evolution of key management and ransomware, we've discussed it in detail in our paper listed on the slide. But what they're using right now, and what's important for the sake of this presentation, is a hybrid encryption scheme, which is called a hybrid encryption scheme because it's a combination of symmetric and asymmetric encryption. So basically, they take a symmetric key to encrypt users' data, but then they use the attacker's public key and asymmetric key to encrypt the symmetric key once the symmetric key is done encrypting the user's data. So that's why it's called a hybrid encryption scheme, since it's a combination of two different encryption schemes. So the diagram over there kind of explains how this is done. The ransomware has the attacker's public key embedded in it. It gets in the host, generates a symmetric key on the host, and then uses that symmetric key to encrypt the files. And then it goes ahead and uses the public key embedded in there to encrypt the symmetric key and safely store it. And the attacker, of course, holds the private key. And there are variations to this approach, but basically, hybrid encryption scheme works in this manner. So let's take a look at implementation details. So we kind of understand how the hybrid encryption scheme works now, but how is it implemented? So to understand how it's implemented, we have to understand how CryptoAPI works in Windows, because that's what these ransomware use. So the CryptoAPI is, just like any other API, provides a level of abstraction to programmers. If you want to do cryptographic tasks, you don't want to be writing all of that complicated crypto code. So there are sets of DLLs that are already available that will let you do this, and CryptoAPI is the way to access those. So CSPs on the other hand, are the actual sets of DLLs that are used for implementing these cryptographic primitives. So CSPs are cryptographic service providers, and each CSP is signed by Microsoft and needs to be validated for it to be used on a Windows host. And they're the ones that actually hold all of the actual functionality that these ransomware need to perform the tasks. CNG, I briefly wanted to mention it because starting from Windows Vista, CNG, Cryptography API Next Generation, has replaced CryptoAPI, but most of the functionality is the same, so everything we're talking about still applies. So this is a very simple sketch of how ransomware communicates with the DLLs on the computer in terms of the crypt functions that it needs. So if we remove all other unnecessary details, like how it spreads like a worm and all of that, and we just focus on the crypto part on the host, this is what it needs. So ransomware, when it executes, it demands access to the advanced API for the crypto functions that it needs. And then that will forward the call to the cryptsp.dll, which is basically responsible for checking the signature of the CSP or validates the CSP. And once it's found that the CSP is valid, it will forward the call to the actual CSP. And the CSP will provide the functionality that the ransomware is looking for. So why use the native CryptoAPI? The simple answer to this is that it's easy for them to do this. There's more of a likelihood to make a mistake if you're trying to implement all of this functionality yourself in your ransomware, and they make mistakes all the time, like I've stated previously. So they want to be using the native CryptoAPI. It makes things easier for them. So with that, let's try to understand the actual CryptoAPI functions that the ransomware is using. So for this, we'll take a look at the NotPetya ransomware. And so this is, once the NotPetya ransomware infects a host, this is the ransom message that you're greeted with, and we're all familiar with this screen. So we went ahead and disassembled the NotPetya ransomware. Once you disassemble a malware, most of the times you'll come across some sort of UPX packing, so you have to unpack the malware. But after that, you can actually read through its assembly code. And so that's what we're trying to do. And what our objective is to identify the actual functions in the DLLs that it needs to execute. So the ransom message is pretty easy to spot, because it's all in text form. Oops, your files are encrypted. And then what follows next is, I believe, the Bitcoin address and the attacker's email address and so on. But that's not our objective here. Our objective is to find out what DLLs it's using and what exact functions it's using in those DLLs. So we use a bunch of tools to identify which DLLs are being used. So if these tools, if you give it the application, they'll tell you what are the dependencies for this application. So we come across two important DLLs over there, Advanced API and the Crypt32.dll, which basically provide the crypto functionality to the ransomware. Then there are some other DLLs on there. For example, the kernel32.dll, that's used for directory traversal while you're trying to find the next file to encrypt, and so on. So those are the list of DLL that the NotPetya ransomware needs. And then we take a closer look at the list of imports, and we see that from Advanced API 32, it's demanding a bunch of crypt functions. For example, CryptDestroy key, CryptGenerate key, CryptEncrypt, and so on. So we want to look at what exactly these functions are doing and why the ransomware needs these functions, and how it's using these functions to encrypt a user's computer. So we zero in on the CryptoAPI calls. Again, there's a lot of stuff going on here. For example, NotPetya also tries to spread by exploiting the SMB vulnerability and so on. So we're leaving all of that aside, and we're focusing on the CryptoAPI calls. So this is like a zoomed out version of the CryptoAPI calls that it's trying to make. And so the first thing that we encounter is CryptAcquire Context. So that's where establishing a crypto context, and we'll discuss the details of what that function does. But that's where it kind of begins. And then it goes ahead and generates an AES 128-bit key. Now, these are all subroutines that we can expand upon, but this is a zoomed out version. Now, this subroutine, generate AES 128-bit key, wasn't named this. Of course, it had a weird name, but we renamed it for the purposes of this presentation so that it's easier to understand what's going on in that subroutine. So once you go ahead and study a subroutine, you can go ahead and rename it so that it's easier for us to then analyze the overall picture. So next, it tries to encrypt user files using a subroutine. Then it displays the ransom message, destroys the key from memory, and then releases the crypto context. So now to take a deeper look at exactly what these functions allow the ransomware to do. So beginning with CryptAcquire Context. So this is the first thing that you'll see a ransomware do if it's using the crypto API, because this is what will allow it to make calls to the CSP. So we just discussed that the cryptographic service providers are the sets of DLLs that provide the actual cryptographic functionality to a ransomware. And so to able to talk to them, it needs to establish a handle to the CSP, and to establish that handle, CryptAcquire Context is used. So let's take a look at this. It acquires a handle to a key container within a CSP, and the return handle can be used to make calls to the CSP. So this C++ code example is taken straight from the Microsoft documentation, which shows how to use this function. So basically, you provided the handle. The address for where the handle will be stored as the first parameter, and then you also specify which CSP you want to use. So the other parameter you see in there is the provider RSA full, or the prov RSA full, and that's one of the CSPs that this ransomware is trying to use. So you can specify the CSP you want to use, and you can specify where the handle to the CSP is going to be, and so then you now have acquired a handle to the CSP, and you can now talk to the CSP. So once you have done that, now you can go ahead and start making calls. So the first call you make is, of course, going to be, give me a new symmetric key, because they need a new encryption secret per victim. So to generate a new symmetric key, so this is a zoomed in part for the generate AES symmetric AES 128-bit symmetric key. So over here, they're trying to generate a new symmetric key on the victim. So this will be unique to every victim, and they'll use the CryptGen key function for this. So this is responsible for generating a symmetric key or a public-private key pair. So this will randomly generate a symmetric key that the ransomware needs, and then a handle to that symmetric key will be returned to the ransomware. And again, there's the C++ example of how to do it. You've got to specify the handle to the CSP as one of the parameters. You've got to specify which encryption algorithm you're going to use. So in this case, the ransomware wants to use the AES 128 algorithm, so it will specify that. And then it will go ahead and acquire the handle to the key stored in that parameter there, H key. So then, you've created a key now. So the next thing you do is very straightforward. You go ahead and use this key to encrypt the user's files. So this is a zoomed-in version of the subroutine, which is responsible for going through the directories and subdirectories and encrypting user files. So we see that they have embedded that embedded part in there where it's talking about the file types that it's interested in encrypting. So the .3ds, .7z, so there's some zip files being encrypted, .asp, .backup files. So there are many file types that this ransomware is interested in encrypting. So we'll go ahead and search through the files and folders for those specific file types. And once it encounters a directory with a subdirectory in it, it will call itself and try to encrypt those. That find next file function that you see at the very bottom, highlighted at the very bottom, that comes from kernel 32 that lets you find the next file and go through one file at a time through a directory. So it's clear what it's trying to do over here, search through the directories and then to actually encrypt the files that it's interested in encrypting, it will use the CryptEncrypt function. So of course at this, I've also put the CryptDecrypt function in this slide, but it's not of course it's not interested in decrypting anything at this point, but they are the exact opposites of each other, as is clear. So CryptEncrypt can be used to encrypt the files, so all it needs is a handle to the key. So the generated AES symmetric key will be provided, and then that handle can be used to go ahead and start encrypting the files. You don't even need to specify which algorithm to use, because the key will specify which algorithm to use. If it's an AES 128-bit key, then it will use the AES encryption algorithm to go ahead and encrypt it. All right, so next thing to do, like we talked about the hybrid encryption scheme that these modern ransomware use. And so the next thing for these ransomware to do is to use the attacker's public key somehow to safeguard or secure this symmetric key once it's done with its encryption job on the victim's computer. So to do this, the attacker's public key is embedded in the ransomware like we talked about before. And that long string that you see in the first highlighted red box is the attacker's public key in the case of NotPetya ransomware. So it uses this. So that's if I remember correctly, that's a RSA 204-bit key, and that public key is used to encrypt the symmetric key. So so right now that is embedded as a string in the ransomware, but to bring it in the context of the CSP so that the CSP can use it to encrypt the symmetric key, we have to use the CryptImportKey function. So the ransomware goes ahead and uses the CryptImportKey function to bring this embedded attacker's public key into context of the CSP, and then frees the memory by using local free. And then so CryptImportKey transfers a key from a key blob to a CSP and brings it into the context of the CSP, and now it can be used to encrypt the symmetric key. So now we've safeguarded the symmetric key, we've encrypted it using the attacker's public key, and now we can. But before we can do that, we have to export the symmetric key to a key blob. And so to do that, this is just the opposite of what CryptImportKey was trying to do. This one is trying to export the symmetric key from the context of the CSP into a key blob so that it can be encrypted from with the attacker's public key. So the CryptExportKey function is used for this purpose. And all you need to do is specify the handle to the key, and then allocate memory for that key, and then do the actual exporting. So this will securely transfer the key from the CSP to a key block. Last thing, and a very important step, is to destroy the key. And believe it or not, sometimes ransomware developers forget to do this, which is why you have websites like No More Ransom, which can make a decryptor for a particular ransomware variant because they've neglected to do, let's say, for example, one of these steps, like wipe the key from memory. If they don't wipe it from memory, or if they leave a copy of it on disk somewhere, then it can be recovered using one of those decryptors. So the point is that they make mistakes. And so if you understand these functions better than they do, then it helps us quickly attack them. So CryptDestroy key is important to execute. Unfortunately, in the case of this ransomware, they did it right, and they destroyed the key from memory. And so it cannot be recovered once this function executes. So CryptDestroy key is responsible for removing the key from memory, releases the handle to the key parameter, and invalidates key and ensures that it cannot be used again. The usage is very simple. You just need to provide the handle to the key, and CryptDestroy key will take care of the rest. Finally, you have CryptRelease Context, and that's the final step that you need to do. And it is an opposite of what CryptAcquire Context was doing in the beginning. CryptAcquire Context was making sure we have the handle to the CSP so we can make all of these calls and access all of these functions. And CryptRelease Context is doing the exact opposite, which is it's trying to release the handle to the CSP so you can no longer make calls to the CSP. So this is the final step that any application accessing crypto functionality using the Crypto API on Windows would need to do. So CryptRelease Context releases the handle to the CSP. You just need to provide it the handle to the CSP, and it will release the handle. So to tie it all together, to put it all together, this is not specific to the NotPetya ransomware. What we were discussing up till now, all the assembly we were seeing was specific to the NotPetya ransomware. But this is a generic pseudocode that we came up with after looking at many variants, many modern ransomware variants that are successful. They all follow this kind of a scheme. So if you go about putting this in the form of a pseudocode, we'll see that it starts with a main function at the top where it will generate the handle to the CSP, and the next thing it will call some subroutines. Each subroutine has a specific task. For example, this first subroutine is responsible for generating the key. So when it needs the key, it will make the call to the subroutine. That will generate the key. So in this, we're using, again, like I mentioned before, CryptGen key to generate the key. The algorithm that is being specified over there is the second parameter to that function, which is the AES 128-bit. And that's what the key is being generated, and it will be stored in that symmetric key variable in the end. And then this function will return the symmetric key generated, and the control returns back to main. Then the next function or subroutine is executed, which is go ahead and start encrypting the files using this symmetric key, and that is go through the directories and find out the file types that you're interested in, the extensions you're interested in, and use the key to encrypt it. Return control back to main, and finally the next function is called, which we call a cleanup function. And this function is responsible for making sure that they encode the AES key or the symmetric key that they've used to encrypt the data, and they encrypt it using the attacker's public key, and that is safely stored on the victim's machine. And then after that, they'll display the ransom note, and then free the memory, make sure that everything is wiped so that the key cannot be recovered. And so in conclusion, we've assumed that ransomware has infiltrated host, and because it will continue to find victims. And what can we do from this point on? Once the files have been encrypted, is there a way for us to quickly reverse the encryption, get victims their files back without paying the ransom, of course? And so the only thing we can do is hope that they made a mistake in implementing key management and use that to our advantage. An empirical analysis suggests, like I said, a study done by Karaz et al. In about 2015. In their paper, they studied about 1,300 ransomware variants, and they found only 6% are effective. So we know that they make mistakes, and they're not the best programmers out there. So that's why it pays to pay attention to key management and make sure we understand it better than they do. And this allows us to quickly attack flaws in ransomware to recover files. And then we can start contributing our own decryptors to efforts like No More Ransom, where we can help victims get their files back without paying the ransom. That's it. Thank you very much.